Hello everyone, sorry for the delay. Today we are going to start the Linear Algebra 101 series, so welcome to that. Let me start with a short intro of myself. I am Mehreen Mallick Fiona. I am studying in Brack University. My major is computer science and engineering. That would be my short intro, and let's start with today's agenda. So today we will learn very simple topics which will help us to translate why we need linear algebra and its practical application. So let's start with that. So what comes to your mind when you hear the word linear algebra? If you can hear me, please do write in the chat box. I'll try to see. So today we will learn what is a system of simple linear equation and how we can use its many of its concepts such as singularity and linear independence, and if we have time we'll try to cover up to determining indeterminate. So let's start. So this was my event banner. So for week 1's learning objective, we will solve system of linear equation because it will help us to know the algebraic methods to find solution and interpret their geometrical meaning and translate the systems into vector and matrices and compute and apply determinant. As I said, we will try to finish all of that. So to begin with the simplest term, what is linear algebra? As you can see, whenever the word linear algebra comes to my mind, it pops a straight line or something linear in figure. So linear algebra is something that deals with mostly vectors, algebra, and set of lines, vectors, and array of numbers which are called matrices. Generally, this. So this simple tree structure or representation of them helps us in machine learning, and because large models or LM models which are computing nowadays are using this smallest unit to compute their accuracy and their prediction model we can do to use to predict it. So that would be all for a short intro of what is a linear algebra for the idea of it. So let's begin. uh, if you are unexpectedly using linear algebra in your day-to-day life, if you are familiar with the line straight line y equal to mx plus b, then you have done some of linear algebra maths in your life. It is the basic equation or a model which is used in linear regression, which we will get idea of it in the near future right now. So let's know about the application of linear algebra in short before we start in today's topic. We can see that in bold there are multiple application of linear algebra. Here we can see from machine learning to computer vision, it helps in multiple areas. I'm not going to elaborate all of them, so you can get a glance of it here. So I'm gonna pause here for a moment so that you can grasp the point. So I'm gonna pause now. Let me know in the comments if you are done with it so that we can continue to our next topic. So as you are seeing the points, I want to say that how linear algebra fits into the machine learning model. As you can see, machine learning is all about making the computer learn about the patterns and everything so that it can do the work for us to predict or detect a relation between them, so we can get a best fit output or a feedback using that model so that it can help us in near future doing research or analysis, anything regarding that now. So it helps us to draw a line between the multiple data set, raw data set. We have to collect a data set, then we have a predefined output, but we want something more feasible than that output, so we try to figure out how it can be more feasible for us and everybody. So one of the application would be linear regression. If I'm talking about now, right now I'm indicating that no. So let's begin to today's topic, which is linear algebra. But before that, I wanted to show you something. Wait a moment. So as I said, linear regression is the most basic one of the example if we are going to start linear algebra. So linear regression is simply a supervised machine learning model which helps us to predict certain output where our input is already figured out and the output also, but we want to determine a more powerful output. So the linear regression is based on the most simplest uh, equation of linear algebra, which is y equal to wx by b. So let's say the x is the input of that feature that we want to predict, that is wind speed of the windmill, and we are going to find out the output, which is the maximum output of power output of a windmill, which would be our goal. So this is the one feature if we want to talk, but we have to calculate or predict this model or our output in a smart way. So we'll add something, a bias value, so there is b. So that's why it is in denoted as b, but in a simple equation, or if we want to do linear equation in basic mathematics, we'll see that it would be C and it would be regarded as intercept. But in case of linear regression, we are denoting it as a bias, to as we are assuming the weight and predicting it, so we are calling it bias. So if we want to plot this, so that would be like, in terms of x-axis we would plot the wind speed, and in terms of y-axis we would predict the value of the wind output, that is of the windmill. So let's say x is the input of feature 1, which is wind speed, and this would be our power output, because when we are using the windmill to generate an output, power output, which would help us to generate electricity. So let's say we have a scattered data here. So we want to, our agenda here is to find the best fit of line. So we will assume that there, let me add numerous dots so that we can assume the base fit line by, and let us assume this is the base fit line. But as you can see, even though it works for now as it is a one feature model, so we can assume that the relationship here is completely linear. So for the sake of this model, we can see that even though it has a scattered plot, but we are assuming that is linear. So as we have an added and weight and a bias value, so for the sake of our assumption, we can completely say it is okay. But what would happen if we have multiple features? So the basic theory of it is simple, because we will just add weight and the feature, first feature, then weight of the second feature and the second feature, then on we can add multiple up to n number of weight and n number of features, but we will get our targeted output, which is y. So we don't need to be, oh, I missed something, wait, we have to add the bias, I forgot that, sorry. So end of the day, regardless how many features we are working on, the concept is same. So we will add the weight and the feature equivalent to it and the bias of it, we will get our targeted output. So we can experiment. For example, if my targeted output I want in my windmill is, let's say, 15,000 kilowatts, or much more than that, or less more than that, depending on the number of windmills that I have, and I want to figure out a feasible output with less windmills in my, because I want to generate maximum power, and maximum power would end up in maximum profit for my company if I want to sell that electricity. So that is a short description of how this linear regression or this simple model is helping. But as you can see, there are multiple features I am adding as I speak. But if what would happen if we are working with multiple data sets? For example, this is in a one data set. So let's say we have another one, we are adding w1, w2, same thing, but how can we differentiate if we want to work with these multiple models? So what we would do is simply add a superscript here one, so that we can differentiate between the data set and we can work with this. So we can identify which data set and which one we are working if we are working with multiple data sets. So but we won't put a superscript here because the bias value would be same for everybody, so we won't do that. But in case of output there would be the superscript. So if we have multiple equation like this, let's say I have another one, another one, this whole thing will be our system of linear equation, because it is constructing a system and giving us a idea of something and helping us to deduct something. But as a person like me, this is very complicated to solve. If I wanted to solve it by a calculator, so how can we use to solve it? As we are machine learning enthusiasts, so we would learn to solve this in a smart way. So we can solve this in a very smart way and simple way, that would be converting them into a vector and matrices form. So as you can see, we have three variables. We can simplify the system by simply constructing a vector here. The vector would be the weight of the features. If you take n number of weights, that would be this one, then that would be multiplied, then we would take the features, row matrix of the features, let's say, but we have to keep the superscript on. I'm being a little bit lazy, I know. I'm not writing everything down because it is very simple, but I'm writing it down for you. I'm not writing everything, but I'm trying to, so that you can understand. I know my handwriting is very bad here, but for the sake of understanding, I will explain you again what I'm writing. So let me write it in a good way. So I don't, so I let me see if you can see the screen. Wait, yes, you can see the screen. Oh, my bad. It could be very confusing because I am writing so many x to the power 1 and 2. I am writing it wrong, but don't do it, don't be me. So sorry for the bad handwriting, guys. So this would be our required am I running out of space? Let's say we are adding the b here, the bias value here, which is a not a vector, but here we are multiplying. This is a vector. Whoa, it is very colorful. Very colorful. And this is the row matrix. And we will get our output, which will be the output of a targeted output. There will be multiple outputs, as we took 3, but we can take multiple here. You can write more. So let me give a dot to understand. Let me give an n here. If I give here n, then otherwise it would be very redundant. There would be no subscript. So this, the output would be also vector, because we are multiplying and adding. We are multiplying a vector, then adding something bias value to it, so it will be a vector. the resulted output vector. So we can solve this by this simplifying method, because if you see this and if you were told to solve, then I would literally panic what to do as a beginner. But if you know the simplification of the system, then you can easily solve this. As it is a supervised learning, you can supervise and use everything and be in every segment of it. You can teach the model and uh, oversee everything here, so you don't need to worry, you can be a part of everything here. So we can use to solve this like that. So is a much more easy interpretation. So let's dive for our next agenda, or the next topic that I want to talk about. I'm not going to lengthen the session because I started very late. I'll try to wrap it up in a short time. So now that we have an idea of what is the linear regression, I have given a very short description of it because we are not going to dive deep into the linear regression part, but we want to do the linear algebra part. So as we get back into it, it is a very basic concept as I have written here, and as I told before, it mostly deals with planes and vectors and matrices, and it is the simple form of it. We are dealing this every day, we are solving simple systems every day, but we do not know it's the application or interpretation of the ML or the linear algebra that can be used in machine learning if we are working with application for analyzing or predicting something. We are using them and to our day-to-day life. So we need to understand the importance of such linear equation because it is helping us to solve practical problems, because engineers are using such models and such features, like number of features. They can analyze a circuit, predict a circuit as I analyzed here, an output, and they can solve the optimization of problem with this, so that can figure out a feasible weight and Bayes value, and so that they can find their targeted output if they're using less resources, and we can model the relationship according to our needs. So let's say I have certain features, for example, I don't have a GPU. So what would I do if I don't have a GPU and I want to use a model to do a prediction or analysis? I can use this such familiar or simplest model to help me, and it also helps in our computer graphics because systematic linear equation are helping them to manipulate and transform such um, images or complicated models day to day. So it is helping us, and understanding such system is very important as we speak, as it is solving a real life problem. So let's start with a simple topic which is very simple, because before we want to learn equation, we have to understand uh, something called sorry, I was checking the chat box, there is no question whatsoever. So let's, enough of linear algebra stuff, let's begin with, oh, was my screen, I don't know if you saw the full screen. Now as I see now, the alignment of it is not clear. So should I go again over shortly or take a glance of it, because I elaborately describe it? Sorry, I didn't notice as I was describing it. So now that we I don't know if you can still see the food. mm. Oh. I think this works, I guess. Yeah, this works. So we took firstly, to begin with, we took one feature, then plotted it against x and y axis, figured out a best fitted line, for assume that the relationship is completely linear. Then we dive into if we have more relationship to deal with or more data set, we will simply use the superscript here and figure out the output. But there is a very simple way to interpret this complex system in form of matrix and vector product. We can simply product and add the bias cell and get our output. This is a much simple way. So now that we will be working such linear system, we need to understand the system of sentences. So let's dive into that. So the system of sentences and equation are pretty much similar, because the equation that we solve from the kindergarten, no, that hard math are not in kindergarten, but as we dive into advanced mathematics slowly from our childhood or kindergarten level, you can see that we sometimes read a certain stem, we understand the stem, what it is saying. Let's say the price of an apple is 10 taka. So what would be the price of if I have 5 oranges, 2 apple, then another fruit. This basic math were there. So we used to picture those fruits and figure out the prices. So we will simply go and flashback to our childhood memories and recall those moments. So before we start, so we are diving to the words of the sentences so that we can understand the system of equation. So to begin with, let me change my screen. I don't know why. Let me check the alignment first, because otherwise I have to regret. Uh, Let me shorten this. So it is now okay, everything is okay. Now I'll progress to begin to understand, sorry, to explain. This is my first time, so I'm very nervous and very so please pardon me. So let's go back to our topic. So as you can see, there are 3 systems here. So the first system, we can see that the cat is gray, very cute little cat, then a cute little dog which is orange. So from this system we are understanding there are 2 identities. And let's see the second system. The dog is orange, the dog is orange, 2 dogs of same color. And in system 3 is the dog is orange and the dog is white. So what are this system are telling to us? So our goal is to find the most informative system which can help us and give us an idea whether the system is singular or non-singular. So if the system is redundant, like here you can see the system 2 is redundant, because I am explaining here, because as you can see we are not getting much of information, because there is only one single entity and there is a repetition of it, because the dog is orange and it is again the dog is orange. We are not getting any visible output or idea of this system. So we are getting one singular information, and as the system is singular, because we are not getting much independent information, and the informativeness of the system is very low, so we are naming it singular, and it's very redundant because the dog is orange and orange, it is not giving us any feedback or a certain meaning of it other than the dog is orange. But as we see in the system 1, the cat is gray and the dog is orange, it is containing two separate information, that there is a cat and there is a dog, so there is no redundancy because there is no repetition of it, and it is dealing with two agents and it is providing us most of the information and all of its information. So we are naming it complete system and calling it non-singular because it is conveying us very all of the four information. As you can see, there are four information. There is a cat and it is gray, and the dog is orange and it is a dog. The identity or the animal is a dog. But in case of system 2, there were only one entity and they are basically describing or repeating the another one. But as you can see in the system 3, the last one, there is a bit change. You can see that the dog is orange and the dog is white. But in case of system 3, if I didn't use the picture, and if they're a dog, end of the day they are a dog, so regardless of the color, it is indicating a entity dog. So a dog cannot be orange and white at the same time, so it is very contradictory and it is not providing us very concrete information of the system. So we are naming it singular. So as you can see, we can say that we got an idea of three kinds, four kinds of information, five, which is how the system is a complete, how it is redundant, and how it is contradictory, and how this is a singular system and non-singular system. So to differentiate between if we were to compare the singular and non-singular one, the singular system can be either redundant or completely contradictory, sorry. And in case of system that are non-singular, that they are mostly free of redundancy and contradictory features. So now that we understood this thing, but we can also treat them as an equation. As I said before, we used to do math that are prices of an orange, and we can simply think of them as x and y variable. Let's say that we have a system, there is x number of cats, so let's say 2x plus 1x, and what would be the total price of them. We can also consider them an equation, but understanding the basic information like how a system becomes complete and redundant, and how it can be contradictory, and why are we saying it non-singular and singular, so it is very necessary to know. Otherwise, when we are dealing with a model or dealing with a data set, and if we want to predict something, we got an output but we do not understand the purpose of it, because the solution of the systems can be kind of three types: no solution, infinitely solution, and there can be no solution. So we need to understand the concept between them, so we will also know about that slowly. So let's do one more testing of this system of sentences. We can see there are four systems. For the first one, we can see that the cat is gray, the dog is orange, the bird is cyan. So we can see there are three complete identities, they are not repetition, so we are terming it as complete and non-singular. But in case of system 2, we can see that the dog is white is repeated two times, and there is a bird cyan, but it is kind of redundant because the dog color is repeating, and it is not giving us much information. As we are dealing with three variables or three entities, we are not getting much of information. Only two information are deducted here, but in system 1 we can see that there are three information. This is the most informative system here, so we are naming it redundant. As the dog is white, it is repeating and it is not bringing new to our table, so it is not giving us any new information. In case of system 3, we can see that the cat is gray, the cat is gray, the cat is gray. So it is only saying the cat is gray. It is not giving us any idea. It is giving an idea of only one system or identity. So we are not getting any extra information, and it is also redundant because it is not a thing but about cats. There is no wrong in that, but it is singular system because it is not bringing new something. But in case of system 4, we can see that there is contradictory because the dog is orange and the dog is white at the same time, but it cannot be happen. It cannot happen because we can not let it happen, as we are dealing with the same entity here, and the color of it and the information of it is contradictory. It has to be same or it cannot be different. So it is kind of contradictory in behavior. Despite we have another entity, the bird is cyan, but it is still a contradictory characteristic and the system is singular. So to recap, we can see that these elements of cats, dog and the bird is helping us to clear the concept of singular system. If we are dealing with, let's say, three separate linear equation here, then we can conclude that whether the system is redundant or complete or contradictory or singular or non-singular. So let's see our system now. As we are moving on, this is the level 3. So in case of level 3, we can see that we are now dealing with system of equation, where you can see I am dealing with two variable. So in case of system 1, we can say that a plus b equal to 10 and a plus 2b equal to 12. So what is the output of it? We can see there is a unique solution which is 8, 2, and they are intersecting each other, and it is providing us an unique information. Let's say the value of a is something plus b equal to 10, but when I am adding the value to b, adding another b, it becomes 2. So the value of b must be 2. So the value of a would be 8 and the value of b would be 2. So we are getting this information and it is giving us much more information. So this is a non-singular system and it is a complete system. Now to the second system, we can see that a plus b equal to 10. Then we can see that twice a plus twice b equal to 20. As you can see, there is a pattern. The a is repeating again, the b is repeating again, and the value is double. So we can conclude that it is simply the same straight line, because let's say the value of a is 10, the value of b is 10, not 10, the value of a is 5, the value of b is 5 also. So their addition of them is 10. So if we take another b and another a, so it would generally get an output of 20. That is simple, and this is very common if we add a value like this. So it is representing the same straight line, so it is not giving us anything, and every single point on this straight line is an unique in number of solution. There can be in number of solution or points, because it can be 8 plus 2, then 6 plus 4, then there would be number of combination that would satisfy this straight line. So it is giving us infinite solution. So it is not bringing us anything but an output of 10. So it is very redundant, as it is providing us the same thing again and again, nothing new to the table, so we can term it as a singular system. But uh, that is the conclusion of the system 2. Now for the last system, we can see that the a plus b equal to 10, but we can see that there is repetition of a and b, but the output is different. But we can see that there is no intersection or a unique solution like the system 1. But we are getting an output, but we are not getting a relationship between them, so they are nothing but a state of two parallel lines. And so as we are not getting any relationship among them, and we are not able to find the separate values of a and b, so we are saying that this system has no solution. And as we are not getting any solution and not getting any more information to the table, there are completely two separate straight lines, we are naming this system as singular. And as it is parallel, so we are concluding its nature as contradictory. So as you can see, these are the common three output that we deal while solving system of linear equation. The solution would be unique, the solution would be infinite, and there would be no solution. So we have to understand and visualize like this so that we can interpret the relationship between them. In case of system 1, we can see that there is a relationship, so we can conduct the values of a and b. But in case of b, there is multiple values of b, their combination are, and their output is same, but their set of different values, but they are generating the same output. So it is nothing but a singular system. If you do not know this deduction techniques or understanding of the system, we would not get any understanding or the output of it, or this understand why it is giving me such output. I have taken two different equation, but is giving me multiple infinite um, inputs, but it is generating the output. Why is like that? So if you know that it is a singular system, and as it is not bringing new information, it is behaving like that. So if we do not know such behind the scene or the backstory of the system, we would not understand the system of linear equation and its purpose. So we will we sorry, we deal here with two variables, but if we were to deal with multiple variables, for example in case of 3 ABC, there would be three straight lines in the plane, and that the equation would be pretty much similar, but they would look different because it is a set of three lines. So let's see, for our next topic would be the linear dependency topic. But before that, let's see we have time or not. Let me see how long it has been. So we are good. Now let's dive into the another topic, our second last topic, like Kerz sir would say. Then Kerz sir is a very nice person. So let me check something. So let's give a short recap for what we have learned for now, or learned a few minutes ago. We learned what is theoretically linear algebra and some of its simplest unit, and what is system of linear equation, some of the representation of it, which is set of lines, array of number, matrix and vectors. Now we also learn how the system is singular, non-singular, and how the system of sentences is, and how can we conclude and how we can what would I say, how we can explain or understand the system, like system of sentences, and how we can interpret the system of sentences to system of equation. Now as we learn how the system is redundant, as it is repeating the same thing, and what, as I said before, that the system of sentences would be like the concept how the system is informative or not, and how it is getting us the idea how it is singular or non-singular. So it is kind of letting us know, or indirectly, to the concept which is linear independence, how the relationship or the entities are independent or dependent on each other, so we can understand the graphs of it. So as you can see that I have taken two example here, short two example, 2 by 2 matrices. We can represent this system of equation or this linear equation into a matrix like this by taking their coefficient and convert them into a 2 by 2 row matrices. So there is 1 1 9 9, and on the right side we can also see there is a system where they have a plus b and their coefficient. So what we are trying to understand here, as you can already deduct that the system 1 here is simply the 9 times of the first one, so it is not bringing uh, new to the system. So it is generally the repetition of the first system but in 9 times. So the rows are linearly dependent on each other because it is the repetition of it, and it is, if we divide the second equation by 9 we would ultimately get the first equation. So it is generally the same thing, so they are independent to each other. But in case of the second system, we can see that despite there is a repetition, but they are not independent because not independent, not dependent, because there is no way we can manipulate the first row or the second row to make each other dependent of each other. We cannot multiple of this or that. Simply we cannot create a relationship between them because there is a two which is making them slightly different and making them independent. But in case of here, there is an easy relationship because we can simply multiply by 9 or divide by 9 and repeat it, and also the same thing we can juggle them up and down, and the system would be same. The 2 by 2 matrix would be same, their transpose would be also the same. But in case of here, even if we transpose this system, there would be a completely new matrix. So it is not giving us any sort of dependency symptoms or characteristics. So as the first system is depicting the linear dependency, we can say that the rows are linearly dependent and it is linear dependency is shown. And on the other hand, on the right hand side, the system is non-singular because it is providing us unique and informative system, two different information and not multiple of each other, and the rows are linearly independent of them, no ways of manipulating them to each other. So we are saying that there exists a linear independence between them. So the understanding of this is helpful because we can understand that how much information is independent, or we can deduct something, because if we were to figure out a very large system, and in future we'll learn about rank. If we know about the concept of linear independence or dependence, then we can easily figure out the rank of a matrix or a system. So we will learn about that in our next section, but this concept will help us to figure out the rank of a matrices, and this rank also indicates the uh, independence feature. I'm giving a short idea of it. We'll understand or figure out how we can deduct rank of a matrices. Now, as I said, we will end our today's session by figure outing the determinant. So we can see that determinant is a set of square matrices and the set of numbers, and it can be real or complex, and it is defined by f of a equal to k, where a belongs to s and k where is a constant which belongs to a real number, and f of a is called the determinant of a. This is a very uh, good definition of determinant, but uh, sorry, so determinant, but we are not understanding anything of it, but as a beginner. So what is this determinant? So determinant is helping us to figure out a certain value between the certain value relationship between the rows, so that we can conclude whether the system is singular or non-singular, which is a very simple way. Previously we did very broad analysis, whether there is repetition, whether there is redundancy or contradictory, but we can simply deduct whether a system is singular or non-singular in a very much pretty way, which is determinant. Because if we conclude determinant is a process where we can get a certain value between the array of numbers in the matrices or the coefficient of the system, so that we can conclude a value which is absolute value. So it would help us to figure out a system is singular or non-singular. Let's say we have a matrices 2 by 2 where we have a b c d, and let's consider a k equal to c, b k equal to d, and now here the k is constant. So if we want to develop a equation like this, like c by a, d by b and equal to k, because there exists a common element between them, k. So now we simply cross multiplication and get this equation. So easy way to figure out if you are dealing with a 2 by 2 matrices, you simply multiply the prime diagonal, which is this one, a and d, the corner one, which is the main primary diagonal, will simply multiply and subtract the opposite diagonal, and the value of it is giving us the understanding whether the system is singular or non-singular. So if we get the value 0, then the system is non-singular. Wait a moment, let me check the chat. So as I said before, I might have said that if we get the value 0, then the system is maybe non-singular, but it is not. I said it wrong. If we get a 0 value, and then the system is singular and the system is very redundant. And as you can see from the previous example, if we take this example for instance, then if you multiply 9, then the output will be 0. So the system would be singular, and it would tell us there is a linear dependency between them, so their output is 0. But in case of a non-singular system, we can see that if we multiply the prime diagonal, so primary diagonal 1 into 1, then minus 2, the answer would be minus 1. So it is giving a non-zero output or a non-zero value. So we can understand the system here, or the matrices we are dealing with is a non-singular one. So it is giving us a very shortcut way to understand whether the system is singular or non-singular, and it is also helping us to deduct whether there is a linear dependence or independence between them. So if you are still unclear about these concepts, so think of this. You are in a hangout, you are no sorry if you are in a group discussion, you are brainstorming about a certain idea or a project idea, everybody is indicating or referring to the same idea. So it is not giving us new output, is resulting into the same thing. So the system is very dependent, but the topic is uh, just repeating another thought, so it is not bringing new to the table. But if anyone can bring a unique perspective to that play, that we are to deduct, let's say someone gave us a very unique idea that has never been seen or done, then it is very example of a linear independence or independent idea or independent system. So it is bringing a new idea and a new information to the table, and it is bringing out the best of it. So that would be all for today, and if you still are unclear about today's session, you can simply let me know in the comments or the chat here. So I hope you were patient and understood what I was trying to make you understand. So thank you for staying till now, and I would try to introduce to you new topics in our next day, so that you can learn more about the linear algebra. And this was just the basic or a scratch to the linear algebra or the machine learning basics journey. So thank you for staying for so long, and I hope you would come back again to the next session to learn more about the linear algebra and its more features, the such as I said rank. So